In this part of the dynamics chapter, we're going to take a look at inclined planes. Now, previously we'd mostly looked at situations happening horizontally or situations happening vertically. Here we're going to consider a slope. So we have here a particle resting on an inclined plane, and we want to think about what forces are acting on it first. So we have its weight pulling it down. We have the reaction force stopping it from falling into the plane. And because it's a rough inclined plane, we have friction stopping it from sliding down. So now we know which forces are acting on it, and these are typically the forces that we'll have to consider in most inclined plane problems. So in order to solve something like this, we're going to need to resolve forces into components. But how are we going to do so? What angles are we acting at? And which directions do we want to resolve them into? Now normally we'd look at doing things horizontally and vertically, but in this case we've got two of our forces not acting in those directions. We'd have to do more resolving. So it actually becomes more useful to instead resolve parallel and perpendicular to the plane. So how are we going to do that? What angle is our weight acting at? Well, we want to put it in. If we draw a line down here, we can see that we've got a line perpendicular to the plane, and if we were to continue the line of action of our force, we can see we've got a right angle triangle here. So we have an angle of theta and we have an angle of 90 degrees. So to find the last angle in that triangle, we just subtract those from 180, and this gives us 90 minus theta. We also know that this angle, this very large angle, is a right angle. So in order to find this part, which is what we want, this angle that we actually want, we want to subtract 90 minus theta from 90 degrees. So in fact, we are just left with theta. Now you won't need to derive this every time you do an inclined plane problem, but you need to be aware that that's the angle that we're dealing with. So now we can resolve our forces, and if we want to get the part of our weight that's acting perpendicular to the plane, we can use mg cos theta, and for the part of our weight that's acting parallel to the plane, we have mg sin theta, because that's opposite the angle. So now we can create our equations of motion, taking perpendicular to the plane, taking out the plane as positive, and taking up or down the plane as positive for our parallel to the plane motion. So, coming out of the plane, we have the r minus mg cos theta is equal to a mass times 0, because our particle isn't floating off of it, we know it's not accelerating off of the plane. So we have the r is equal to mg cos theta. Resolving forces parallel to the plane, taking down the plane as positive, we have that mg sin theta minus friction is again equal to 0, because in this case we're assuming that our particle is sitting at rest. So then we have that f is equal to mg sin theta. So then if we take these two results, we plug them into our relation between friction and the reaction force, we have that f is less than or equal to mu r, because we know the particle is at rest. So substituting in our equations, we have mg sin theta is less than or equal to mu mg cos theta. So since we've got m and g in both of our terms, we can cancel that, dividing through by m and g to remove them from our equation, and that leaves us with sin theta is less than or equal to mu cos theta. So then we can divide through by cos. We've got sin theta over cos theta is less than or equal to our coefficient of friction. Now you will learn later in C2 chapter 10 that tan theta is identically equal to sin theta over cos theta. So we can then rewrite that as tan theta is less than or equal to mu. So then we have that if tan theta is less than or equal to mu, then the particle will stay at rest. And we're not going to slide down the plane at all. But if tan theta is greater than mu, then the particle will accelerate down the slope. Now this is generally true for all inclined planes, and it's independent of the mass of the particle. But if we have other forces happening, then the situation changes. So let's now take a look at a couple of examples. So here we have a particle held at rest on a rough plane, which is inclined at an angle alpha, and we're told what tan alpha is. We're also told what the coefficient of friction is. So, as with many mechanics questions, we want to start by drawing a diagram. So, we have our inclined plane, inclined at an angle alpha. We have our particle with an unknown mass, so let's just put mg as its weight. We have the reaction force, and we have friction. Now we're told it's going to slide down the plane after it's released from rest, so we know that friction is going to be acting up the plane. Now, since we know that tan alpha is equal to 3/4, we can draw a right angle triangle and then work out what sine alpha and cos alpha would be. So since tan alpha is opposite over adjacent, we know that the opposite is going to be 3, the adjacent is going to be 4, and then by Pythagoras we can work out that our hypotenuse is going to be 5. So this tells us that sine alpha is now equal to 3/5, and we know that cos alpha is equal to 4/5. And we can use this in forming our equations. So, if we resolve perpendicular to the plane, we get r minus mg cos alpha is equal to 0. So then that tells us that r is equal to 4/5 mg. We can take mg cos alpha over to the other side, and we know that cos alpha is equal to 4/5. We can then resolve, in this case, going down the plane as positive, since we know it's accelerating down the plane. So we have mg sine alpha minus f is equal to ma. So we have that 3/5 mg minus f is equal to ma. So to solve this, we then need to relate friction to the reaction force. We need to make use of the coefficient of friction. Since the particle is accelerating, we know that f will take its limiting value, so we'll have that f is equal to mu r. So then f is equal to 0.5 times what was r, 4/5 mg, so we have that f equals 2/5 mg. So we can then substitute this into our equation for motion parallel to the plane. So that gives us 3/5 mg minus 2/5 mg is equal to ma. So So we have mass appearing in each of our terms, so we can cancel that. So we can divide through by m in order to get rid of that, and then we can subtract our two terms. And that leaves us with 1 over 5g is equal to a. So, plugging that into our calculator, that tells us that a is equal to 1.96 meters per second per second. But since we're dealing with g, we could consider rounding to two significant figures. So we might want to say is equal to 2.0 meters per second to 2sf. Now that we know how fast the particle is accelerating, we can work out part B. We can work out how far it's going to slide in the first 2 seconds. So, we know what A is. We know what U is because it was held at rest to begin with. We're looking for it to happen in the first 2 seconds, and S is what we're trying to find. We're trying to find the distance. So then we want to make use of a Suvat equation. And it's fairly common for a problem on forces to suddenly turn into a Suvat equation. So we're going to look at S equals ut plus a half at squared. So that gives us S is equal to U plus a half times 1.96 times 4, which is 2 squared. So that gives us S is equal to 3.92 meters. And because we've made use of G, we want to round things to two significant figures. So we have that S is equal to 3.9 meters to 2sf. So, that's how we can deal with one sort of inclined plane problem. Let's take a look at one more example. So this time we have a box sitting on an inclined plane that's being pushed up the plane by a horizontal force of 25 newtons. We're told what angle the plane is at, and we know what the coefficient of friction is, and we want to find the acceleration of the box. So again, we want to start, as with all mechanics questions, by drawing a diagram. So we're inclined at 10 degrees. We have our box sitting on the plane, and this time we know its mass. We have our reaction force stopping it from falling into the plane. We have our horizontal force that's pushing it up. And to give myself a little space, I'm going to put friction here this time. It's still acting down the plane, it's still opposing motion, because we're told that it's trying to push it up the plane. But this gives me a little more space. Now, we have our forces, we know what angle our weight is going to be acting at, but we need to think about what angle that force is going to act at, because that's going to come into how it's going to affect our equations when we resolve perpendicular and parallel to the plane. Now we know through alternate angles, since we've got a horizontal force that's parallel to the ground we've got at the bottom, so we know that this angle is 10 degrees. So, now we can resolve forces. Let's start by resolving coming out of the plane as positive. So that gives us r minus 2g cos 10 minus 25 sine 10 is equal to 0. So that tells us that r is equal to 2g cos 10 plus 25 sine 10. So next, let's resolve going up the plane, since that's where the direction it is accelerating in. And we get 25 cos 10 minus 2g sine 10 minus friction is equal to 2a, because we know that it has a mass of 2 kilograms. So, as is often the case, we'll need to make use of F equals mu r in order to continue. So we have F is equal to mu r, so F is equal to 0.3 times 2g cos 10 plus 25 sine 10. And we know, since the box is accelerating, friction will take this maximum value. So we can substitute that into our previous equation, and we get quite a long expression. We have that 2a is equal to 25 cos 10 minus 2g sine 10 minus 0.3 times 2g cos 10 plus 25 sine 10. So we need to be very careful putting this into our calculator at this point, and the reason I haven't computed some of the parts of this as we went along is because I didn't want to use rounded values. I want to be using the true values all the way through, so I don't get a small error coming in. So plugging this whole long expression into our calculator, we find that it comes down to 14.12366. So then, dividing by 2, we get that A is equal to 7.0618, and then because we've made use of G in our calculations, we want to round to 2 significant figures, so A is equal to 7.1 meters per second per second. Now that we've had a look at a couple of examples, it's time for you to have a go at exercise 3E, or if you're feeling very confident, have a go at these questions as well.